Okay, so we're moving to BCC now. Here's the diagram showing the partials that constitute a 111 slip on the 110 plane in a BCC. Now that is fine. There are three possible slip planes in the BCC, as I showed earlier. This is the main one. But what's more important is the Martin-Sittig transformation. And to illustrate the Martin-Sittig transformation in BCC, I'm going to show you here. One can construct an orthorhombic cell if we think about the cube, which constitutes here's four cubes, which are the body-centered cubic structure. These are the atoms at the center of each cube. If we now construct an orthorhombic unit cell on that cube, we can think of the layers as an A and a B layer. So A, B, A. And so the arrangement of the atoms on this top layer are shown here. And when one wants to move to a using this orthorhombic basis, if one wants to shear, one can shear every other plane, let's say this B plane, relative to the other planes, and actually change the crystal structure and move it into, with a little bit of a shuffle, into a hexagonal type cell. So let me just stop presenting so I can illustrate that. Here we have that same diagram, and I've marked the A and the B layers. If I get this correctly. As they are in the diagram. And then if I just simply shift one of the layers with respect to the other one, like that, the balls are sitting in a more low energy state, and this now is closer to a hexagonal structure, closer to the basal plane, and ABA stacking. So let's go back to presenting. So that's an important point to know, is that it's relatively easy to, by a shear, to get from the BCC state to the hexagonal close-pack state. Oh, and I should mention, just like with the FCC and the HCP epsilon Martensite transformation, which is reversible, by the way, it goes one way and the other. The same thing applies with the BCC and the HCP, in that the transformation occurs when one does the shear on every successive plane. So it's not like a twinning operation, although one could, in principle, create a twin on this plane by shearing, because the partials would work in each case. One could twin on basically the 100 plane, but in this particular instance, we're talking about Martensite, and it's every successive plane. The other way, the form of Martensite that is probably most common, and it's very confusing because often people just talk about Martensite and they don't specify what Martensite. And the one that most people in the steels community will be aware of is the Martensite you get from quenching. And that comes about because you quench carbon into these interstices in what would otherwise be a body-centered cubic structure. And this stretches the BCC cell, becomes body-centered tetragonal, and it's a harder phase. This is the BCT form martensite. However, if you form BCC from an epsilon phase or HCP, it would still be called martensite because you created it by a displacive transformation. So the difference between a martensite transformation and any other, I should have mentioned that clearly at the beginning, is it's a diffusionless transformation. It is a displacive transformation. So there are three types of martensite. There are the BCT form, the gamma alpha prime, the BCC form, the alpha, and the epsilon. Now, you only call them martensite if they were created by the displacive transformation from another phase. And this guy, Moore, has done a nice job in summarizing the kind of transformations one can get. You can start off with austenite. You can create faults, and that would be like a Shockley partial shear. And then if you carried on the fault on each successive plane, if you sheared on each successive plane, you get a twin. But you can also create, if you make that fault happen on every other plane, it becomes an epsilon martensite phase. And then from this epsilon phase, from the hexagonal phase, as I've just shown you there, you can actually get to a BCC form. Now, in this case, the martensite, it can be BCC or the alpha prime, depending on how you wants to denote it. You can call it martensite, or you can call it just getting back to the body-centered cubic structure. So why are they important? Well, because they crop up so much, these structures, and they're hard phases, whether it's a martensite or a twin. There are inhomogeneities in effect in the structure, and the more that you deform a material, when you go to higher and higher strains, the more you will get different degrees of twinning and martensite formation. So that's important because that's what you get when you're manufacturing these components, and that can have a profound effect on the embrittlement of the material during irradiation. Okay, so I'm going to move on now quickly to radiation damage. I want to give you a brief introduction about radiation damage for those of you who may not be that familiar. So the one thing that changes the properties of the material in a reactor is the creation of atomic defects, displaced atoms in this particular case. So what we have is a fast neutron comes in, hits an atom. That atom gets knocked on. We form then what's called a collision cascade from this primary knock-on atom, it's a recoil, and you end up with a whole bunch of interstitials and vacancies. Now, these point defects can either recombine, in which case the material heals, or they can go off and create new and form clusters. When they form clusters like that, that adds to the hardening, increases the yield strength of the material. I'll talk about that in a minute. Not only can fast neutrons create displacements, but thermal neutrons can as well. And iron, chrome, and nickel all have a fairly reasonably high thermal neutron capture cross-section. So you get this additional displacements that occur, even though the neutron energy itself is very low. It's in the thermal range. It's less than 0.5 eV. But just simply by absorbing the thermal neutron, when the atom kicks out a gamma ray, there's a recoil. Sorry, I've gone the wrong way. There's a recoil. I clicked on too many there at the same time. There's a recoil, and this creates displacements. Typically, if it's simply N-gamma reaction, the number of displacements is about half a dozen, 5 or 6, and but it's a contribution to the displacement damage, especially in a high thermal neutron environment. But if you then get if you have nickel present, the initial absorption can create nickel 59, and then you have the possibility of a whole bunch of other reactions, the NP and the N-alpha reactions, which can be extremely damaging. So when you have nickel there and you're in a high thermal neutron environment and you have enough time to build up nickel 59, then you end up with a situation where you can increase the damage rates substantially. Not only that, this alpha particle is a helium nucleus. So you get helium embrittlement and a vastly elevated displacement damage. So nickel is very important, and even if you have 10% roughly, or as you would in a nickel alloy, sorry, in a steel, that can be significant if you have sufficient thermal neutrons and if you wait and you have a sufficiently high dose. Thinking about just simply displacements, though, here's a diagram showing the displacement cross sections. That's how many. It's a measure of how much damage you get per neutron for different elements, nickel, iron, chrome, and I put zirconium on here just to show how good zirconium is and why it's used in the Kozak-Candu reactors where we only have natural uranium. You want fewer of these absorption events as you can, and zirconium is particularly good at having a low thermal neutron absorption cross section. And in order to understand how this relates to a reactor, we have to consider how these cross sections coincide with the neutron flux. So I've got a PWR fluxes here in the core. It's a core average, and then this is the last water node just inside of the pressure vessel. And at the low energy range, you have N-gamma reactions creating the damage, and in the high energy range, we have elastic interactions, which are those direct displacements I showed a couple of slides ago. The N-gamma reactions are quite weak. They only create a few displacements, but the knock-on atoms, the direct displacements for neutrons when you're getting up to the MeV range can be hundreds of displaced atoms per event. I mentioned a little bit about nickel. I put zirconium in the title there. I got to take that out. I mentioned a little bit about nickel, and yeah, so when you create enough nickel, it can be another additional contribution to the displacement. But more importantly, nickel 59 is a very high cross section for N-alpha, which basically means it starts to produce, enhances the production of helium. So what we see here is the N-alpha cross section of nickel 59 in red. Once we have, in this particular case, it depends on the amount of nickel 59 you have in that. And so I've scaled this relative to the relative to what would be the amount of nickel 59 you would get after 5 or 10 years in a PWR, about 3%. And I've scaled this, and it's relative to the nickel 58. So this is at the peak nickel 59 production, and the nickel 59 is produced from the nickel 58. So it just shows that once you got sufficient nickel 59 present, there's an possibility then to get a lot of helium embrittlement or helium production. This also shows that nickel 58 has a high N alpha cross section. So even if you have a fast neutron, like a fast reactor, even if you're in a fast reactor and you have a lot of nickel, you're still going to be producing a lot of, or some helium simply from that reaction. So let's talk about loops. I mentioned about displaced atoms and how they create damage. So here's a slide I took off the internet, off YouTube, by Robertson's group, showing what dislocations moving in situ in a steel sample that's pulled without any radiation damage, without any displacement damage in there. And this is what happens once you irradiate it and then pull it again. And it just shows the hardening effect, basically the radiation damage, which is invisible here. It's so small, but it basically impedes the motion of the dislocations. This has implications both for the strength, but also for the creep of the material. So here's an illustration just to show what I mean by the damage. Is that, sorry, I've chosen zircaloy, but because I happen to have a picture of it. This shows before irradiation and after irradiation, roughly the same magnification at 300 degrees C. And these little blobs of contrast are dislocation loops. And what do I mean by dislocation loops? Well, we can take the vacancies, the holes that were left from the displaced atoms, and they can accumulate in disks on a given plane, on a close spec plane. And that would be a vacancy loop, or the interstitials, and they can be pushed in between the planes and also create a dislocation loop. Now, how do these loops change the properties? Well, the evolution of these loops occurs with increasing dose. So, and you reach a steady state condition typically. And what that does is it increases the yield strength. So with increasing dose, we increase the yield strength till we reach a saturation value. And I'm not talking about that here, but suffice to say, empirically, one sees the effect of the loop formation on the hardening of the material. Here's a function, showing the hardening, the yield strength as a function of temperature for a given dose, between 3 and 20 dPa. And one thing you notice is that the hardening effect is less effective at low temperatures compared to higher temperatures. And it goes through a peak, and then as you get to higher and higher temperatures, the difference between the radiation supersaturation and what would be the normal thermal point defect concentration becomes less and less, and the density of the loops and the hardening effect becomes lower. In some situations, you can get very low. You can get to a point where you have recombination dominating. So if all of the atoms are, or most of the atoms are recombining, the displaced atoms are recombining with the vacancies, you have nothing left to create damage. So if you're at one temperature, you do get cluster formation and hardening. And if you're at a low enough temperature, you get healing, recombination, dominating, and therefore there's little effect from that. So how is this manifested in a stress strain curve, this hardening effect? I showed you these earlier. And here's the actual curves that these were generated from. And what is it physically? Well, what you actually see, I mentioned previously that we have this strain drop, this load drop. Sorry, it's a load drop that occurs when the material yields. And what's happening there is that you're applying a stress, you're increasing the stress, and eventually the material will give. So it's very difficult for the dislocations to move through the lattice because you've got all these loops there. But at some point they will be, the dislocations will interact with the loops. And what they actually do is that they sweep out the loops and create channels through the matrix. And actually, as you can see, there's loops here and none there. They've been swept out, and that's actually softened the material, and that's the reason for the load drop. So in a tensile test, I mentioned about the constraints that a tensile test can impose. So if you're shearing in one direction, you get some off-axis load offset in a tensile machine, and what that can induce is a slip on a secondary plane to basically realign the sample, and that creates a second load drop. And what I mean by that, to illustrate that, if you have shearing here, it's kind of distorting the alignment of the tensile specimen. But if you shear on another plane to keep the deformation symmetric and aligned along the load line of the tensile specimen, what you end up with in this cross configuration, you will end up with no minimizing any stresses, elastic stresses, which would otherwise bend the sample. So what do we see when we? Oh, that's not very good. What do we see in detail? What's happening in these channels? Well, there's some residual dislocations. You can see some residual loops. This is a typical channel. Unfortunately, it's zirconium again, but it just gives you the idea. And what I want to point out is it's kind of messy, a little bit messy. The edges of the channel are kind of ragged, and that's because the dislocations are moving around and they're climbing and they're interacting with loops and they're sweeping them out, just like we see down here, which isn't showing up very well, unfortunately, on this configuration. Just the way that this presentation's configured. I don't know what's happening here, why this is so running off the edge of the slide. Anyway, dislocations interact with the loops, sweep them up, carry them along with each other. And when they do that, they climb. They actually move off their slip plane. It's like cross slip, if you like. And that creates a thicker, broader volume layer of material, which is essentially reduced in dislocation, softened. So this leads me to something which I need to point out, or I'd like to point out, and that is twinning. What happens if you get twinning in these situations? So I've just shown you there how dislocations gliding through a material can soften it, create these channels, but they're kind of ragged, and you can see dislocations there. But what I've seen in the press and the publications is nice, clean channels, and the authors describe them as slip bands, which or channels, dislocation slip channels. And that really doesn't make much sense. Here's an example here in A286 with gamma prime, where you have these cleared, I would say clear of contrast, these bands that are clear of contrast, of the gamma prime contrast in this particular case. And in this case, here's some radiation damage, and we have these bands that are clear of contrast. Now, that's not to say, in my mind, that there are no defects in there. What this says to me is that, well, if this is a twin, then the diffraction conditions that exist here do not apply here, same way as here. The diffraction conditions that apply here do not apply here. And in this particular case, this author, Onshi, even talks about twin faulting being observed at the edge of the bands, but he still doesn't call them a twin. And it's, to me, that's kind of somewhat bizarre. So without defining the diffraction condition, it begs the question, are we talking about twins here, or are we talking about actual slip bands, or channels, sorry, which is separate from a slip band. A slip band is a planar process, but a channeling in the way I described just now is more of a bulk event, like a twinning, but it's not. It only becomes bulk because the dislocations are sweeping up dislocation loops, and therefore climbing and moving around and changing their plane as they move through the crystal. Okay, so let's talk about precipitation hardening. I could have maybe blown that up a little bit, but I don't know. Anyway, I have my doubts about things like this, and there are many, many cases in the literature where people talk about dislocation channeling, but are they really identifying it correctly? I have my doubts. Okay, let's talk about precipitation hardening. Here's the classic picture of precipitation hardening. Precipitates, like loops, inhibit dislocation motion, and the only way for a dislocation to get through a field of precipitates is either to cut them and then pass through and they create a step of the dislocation, or to loop around them in what's called an R1 loop. And typically what you will find is the strength of the material is dictated by the precipitate size, but when you're creating precipitates, especially for a precipitation hardened alloy, the more that you anneal it or age it, the bigger the precipitates come, but then the distance between the precipitates increases. And therefore you get to a point where you can loop around it when the separation of the precipitate is large enough. You get what's called R1 looping. So the delta increment in strength is geometrically related to some function of basically this lambda factor, which is the spacing between the dislocations, and some other strength factor which relates to this, in part to this kind of cutting mechanism, but also is a complex combination of the geometry of the precipitates and their spacing. So this term here, that's the number density, and the diameter of the precipitates basically relates to the spacing that one gets between the dislocations. And this alpha has to do with the quality of the ability of the precipitates to inhibit dislocation climb. Now that applies both in R1 looping and in the precipitate cutting. Here's an example from Tan and Busby showing the quality factor, the size effect factor, the quality factor, that alpha strengthening factor, as a function of size. And what we're really talking about then is this part, in effect. And it just shows how different types of barrier to slip, how their size factor, how the alpha factor, the hardening effect for a given precipitate size, how it varies for a given size, how it varies depending on the type of precipitates. Surprisingly, cavities are way up there. So you'd think the cavities wouldn't be much of a barrier in hardening, but yes, they are. So as I said, it it's a little bit more complicated than that. You've got this alpha factor, but in a polycrystalline material, you've also got the fact that you have interactions between different grains of different orientations. And what that means is that the polycrystal can't yield easily, because even though one grain might be oriented in such a way that it can shear, it has a low what's called a Schmidt factor. The neighboring grains, which also have to shear, are constraining it. So in effect, what happens is that the whole material has to be conformal in how it deforms, and that in effect raises the yield strength. And typically, what's applied is a Taylor factor, which takes into account the need to have compatibility of strain between different grains. The actual quality of the barrier, this alpha factor, is also important. I'm not going to talk too much about this. It's just there for reference. So here's I can't remember where I got this slide, but got this table. Look it up on the internet. There are different combinations that different authors have come up with for the strengthening effect. All you need to know for the purposes of this discussion or this presentation is that there's a quality factor, if you like, and a length. And this is how they relate for different types of barrier. Okay, let's talk about swelling. Swelling. So swelling is an issue for certain components, mostly in fast reactors. And steels in particular have a high propensity for swelling. Now, work conducted in the 70s, this is with iron irradiation now at 625 degrees C, showed that the amount of swelling one gets for a given set of conditions decreases as you increase the nickel content. So steels, unfortunately, are up there, and they have a high propensity for swelling. Later work by Garner affecting neutron irradiation as you increase the nickel content, but also Garner showed that as you go to higher nickel contents, the swelling actually starts to tick up again. Now, no physical process can go down and then up if you're only changing one variable. So there has to be something else going on here. There has to be two variables at play in this particular instance. So in this particular case, it's likely that the formation of helium at higher nickel contents, even though it's a fast reactor, that nickel has an order of magnitude N gamma and alpha reaction, even for nickel 58, which is the most common isotope. So that's possibly something that can be at play here to result in this uptick as you increase the helium. But generally, rule of thumb is as you increase the nickel content, the swelling drops down. I'm not sure anybody really understands this too well. It may have something to do with surface energies. Some other point defect properties. I think all I've seen in publications is just a vague allusion to some effect on point defect properties. So one thing which is pretty well established now is that ferritic steels are less prone to swelling than austenitic steel. So we saw there how the austenitics are right up there. And having higher nickel content is, for an austenitic alloy, helps. But What about at low nickel contents and a ferritic steel? Well, you also have low swelling in this particular case. This may be microstructurally because the ferritic steels have different microstructures, but also you've got a body center cubic dominant structure there. So there are a number of reasons why the ferritics are lower swelling. Here's some data from Ghana showing the amount of swelling that you get with increasing fluence at different temperatures. The thing to bear in mind here is the swelling is not only dependent on the creation of cavities, but also on the dislocation structure, which here we're using yield strength as a surrogate for dislocation structure. The lower the yield strength, the lower the dislocation density typically. And what you have to bear in mind is as you go to higher temperatures, you're actually recovering the microstructure. So you actually, it's a secondary effect of the irradiation conditions, if you like. You're not just hardening it, you can actually be softening the material just simply by having it at a higher temperature. It's only at temperatures lower than roughly 400 degrees C do you end up, or 500 degrees C, do you end up actually getting into that regime where hardening becomes dominant. And this all has to be taken into account if you do swelling models. So Bhattacharya and Zinko made a nice summary of both the cavity diameters as a function of irradiation temperature, but also the cavity number density as a function of temperature for both voids, which are considered to be I'm not going to get into this, but for both for voids and for bubbles. In effect, bubbles have a lot of helium in them. So, and voids don't have too much helium in them. So voids are closer to a thermal equilibrium state and bubbles are closer to a non-equilibrium state. And there is a subsequent increase in the number density of the clusters, vacancy clusters in effect, in the case of the bubbles. So when one makes the transition, both with temperature and or helium content, one can model the behavior, the swelling behavior of materials for a given set of conditions. And this just shows some outputs, typical outputs of these models. And they depend largely on the amount of helium relative to vacancies you have. So if you have a high helium to vacancy ratio and have a low temperature, it doesn't really matter too much. You still get mostly small cavities. Whereas if you have a high helium to vacancy ratio in the cavities, then the growth rate can take off at higher temperatures. And higher temperatures, you end up, you're in a basically what's called a bias-driven swelling regime, in which case you can get bimodal distribution. You can get cavities growing at large cavities growing at a certain rate and small cavities growing as well. Here's just a throwaway item just so that how one would model this. And this is just the results of a piece of work I did with some colleagues, Juan Ramos Nervi, and with the help of Larry Greenwood. And this just shows the relationship between the predicted swelling rate from Garner's data and the measured swelling rate from Garner's data and the predicted swelling rate that we get from a model. And as part of that model, it employs freely migrating point defects. And this is an example of the type of calculations one has to do to calculate how many freely migrating point defects there are after you've displaced all the atoms. That is all the number of defects that are left to migrate to sinks after the collision cascade. You can apply that model, show the relative swelling rate, whether it's true or not, of a PWR relative to a fast reactor, EBR2 in this particular case. Okay, let's move on to helium embrittlement. Oh, sorry, let's look onto radiation embrittlement. So one form of embrittlement that's been touted over the last 20 years is a thing called channel fracture. So channel fracture is something which shows up at high doses and is basically typified by planar failures, planar separation of the not intragranular failure, but some failure in a planar mode within the grains, and this has been deemed channel fracture, and it was explained, or has been largely attributed to these shear bands that we talked about. But the shear bands we talked about have to do with softening of the material in narrow bands that can be envisaged as localized deformation, which essentially reduces the ductility. But when you look at these shear bands, and what happens is, and the evidence for these shear bands and the channel fracture is shearing of cavities, which are deemed to be very high strain. But other work has shown the same kind of shearing of the cavities, and in this particular work, back in the 80s with Linda Horton at Oak Ridge. I'm sure she was working with Jim Bentley there, so I'm pretty sure that they would have known that they were dealing with twins in this particular case. They identified twins as being responsible for the shearing. In this case, there's no mention of twins. The belief is that the shearing occurs because of dislocation channeling. But then that would require, because of the nature of the shearing that we see, that you have slip on each successive plane. But that's exactly what a twin is. It's in a much more likely explanation for the kind of channel fracture that has been observed is that the material is full of, or has grains within it, which are martensite platelets. And these are inhomogeneities and sites for failure. And that's all I want to say about that. That gets into a whole new debate and lecture. So as I said earlier, fracture is often associated with swelling. And part of the reason for that is because of images like this, where people see cracking in material with a high density of cavities. But you'll notice here in this particular case, the cracking occurs in a non-linear fashion, so it can't be associated with any channel fracture, as we say. In this particular case, the cracking is occurring along a boundary. And interestingly, the authors say that the cavities are not on the boundary, but somewhat separated from the boundary, which doesn't make much sense. Right? Having cavities, swelling, and a propensity for easier cracking is not hard to imagine, because the normal form of ductile fracture involves the creation of micropores just by nature of the cracking process, and basically pore cavity coalescence. The way that this happens is just basically by slip. You get a crack, you'll get some emission of dislocations at the crack tip. This extends the crack, opens it up, and extends the dimensions of what would be you can call a void. Okay, so now we're going to move on to helium embrittlement. Here's an example of helium embrittlement in Inconel 600. You can see the little mesh here of lines, which are essentially where the dark blotches are where helium bubbles were. Anyway, the essence of helium embrittlement amounts to what helium does. Well, what helium does is it stabilizes cavities on grain boundaries. In this case, we got 316 stainless steel with He ion irradiation and tested to rupture at 750 degrees centigrade. In this instance, we got some ion irradiation. This is the ferritic stainless steel that's subject to ion irradiation at a high temperature. And you'll notice there's lots of swelling, but nothing on the boundaries. And that's because without helium present, the vacancies are just absorbed. So cavities do not form on the boundaries in the absence of helium, but helium stabilizes the grain boundaries. Vacancies which form cavities are absorbed by the grain boundaries, but not when helium is present. So this latter thing, picture here, is some work by Schroeder and Batalski on creep ductility. And taking data from these sources, we see that as you increase the helium content, the amount of creep that one needs before, the amount of strain before the material fails, decreases. So it just shows that that's one aspect of steel operation, especially in fast reactors and Gen 4 reactors. That's important because creep ductility is something that shows up at high temperatures. But what about power reactors? In the power reactors, recent data has shown that even in power reactors, we can get some bubble formation on grain boundaries. And that is associated also with a propensity to more intergranular fracture. So in this particular example, from some work by Fujimoto and Edwards et al., you only have 600 or so APPM of helium, and I think it was after, it's a flux thimble, and I can't remember the number of years operation, but 70 dPa, 625 ppm, I don't know, maybe 20 years, something like that. They found that there was a high density of bubbles on boundaries and a commensurate intergranular fracture. A little aside, a lot of people say, oh, nobody realized about these because people didn't have the focal conditions correct during doing the electron microscopy. And I've heard it said that the key is to do defocusing. Well, I think that's nonsense, frankly. It has to do with having a well-aligned microscope. You have to be aligned with a high resolution. Your spherical aberration has to be minimal, and you focus and defocus as by nature in doing microscopy. So I don't believe that for 1 minute, that the fact that people tended not to report this kind of thing until as late as the mid-2000s because they didn't see them, because they didn't defocus. I think it's more because the microscopes that tended to be used for sacrificed, if you like, for looking at highly radioactive materials tended not to be the high-end microscopes and the costly ones. So ones that you could afford to sacrifice and get contaminated. And in those cases, they may not be that well aligned. So to me, it seems more likely that these things were not apparent in a normal PWR component until this late in the day, 2005, simply because the microscopes that were used in hot cell areas and stuff like that were not the best. Did some work in the last couple of years with this guy, Mike Demkowitz, and he did a very nice job at looking at the effect of grain boundary coverage on the fracture toughness. And he showed basically you don't have to get too high, roughly about 20% coverage, and the fracture toughness basically drops to 0. Okay, so apart from bubbles on boundaries, helium stabilized bubbles on boundaries, what are the other sources of intergranular cracking? Well, one that's cited often, although I'm not sure there's any practical evidence for it, is what's called Stroh type cracking, in which case you get a slip band and a buildup of dislocations at a boundary, such as a grain boundary. And the principle is that if you get sufficient dislocations built up, it becomes a super dislocation and actually is a crack then in that case. However, if you do the calculations, the shear stress needed to push 2 dislocations together is double that. It's like 40 gigapascals. I mean, it's just astronomical. So the likelihood of this kind of thing happening, I think, is just it's purely theoretical. Or if you have a really high stress, I should say. Okay, so I'm going to finish now. I've got 20 minutes left. I'm going to finish now and talk about stress corrosion cracking. You've probably all seen this kind of thing where stress corrosion cracking is a combination of 3 things. It's the environment, the stress, and having or the mechanical loading, and having a susceptible material. If you're irradiating, you get a whole bunch of other additional factors, not least irradiation hardening, and chemical changes, and also in terms of the corrosion, you've got the effect of the ionization from the gamma rays. So as a subject, it's when you think about it, you have tons of variables, and it's very difficult to pin it down and being able to account for all of these variables at once, or even control them so that one can study any one individual variable. So the science of stress corrosion cracking is somewhat of a black art, although certain ideas exist and certain notions about how the cracking process occurs seem reasonable and are reasonably well accepted. So S.P. Lynch, I guess I took this from, he did a schematic here to show the different ways in which you get initiation of these things. So the thing is with stress corrosion cracking, it's a combination of both initiation and crack rate. And this is a diagram which shows, or a schematic figure which shows typically shows the growth rates as a function of the stress intensity factors. So if you have a flaw, a crack, or even a free surface or anything, in order to create the crack, there's a certain stress intensity for a given applied stress at which you will get into the mode of stress corrosion cracking, where you get this more or less constant crack rate as the crack advances. And eventually, as the crack gets too high, or when the crack gets to a very high value, the critical crack length is exceeded and the material fails. This plot is very similar to the plots that's used for delayed hydride cracking in zirconium alloys. In that case, in the zirconium alloys case, the cracking comes from hydride cracking, but they have some commonalities in that they both involve the formation of a brittle phase at a crack tip. In the case of FCC and ISC in LWR reactors, the brittle phase comes about from oxidation at the crack tip, and that comes from the environment, the coolant, oxidation reactions that are occurring at the crack tip. But in the hydride cracking case, the hydride formation at the crack tip comes about from diffusion of hydrogen through the matrix, which is somewhat related to the corrosion, because the amount of hydrogen in the matrix is a function of the pickup from the corrosion itself. So we end up with this condition where if it's a blunt crack or a free surface, you won't get any cracking formed, but at a certain point you can get some cracking started, and once you get the cracking, it progresses in a constant, more or less constant manner until you get to this to get this exceed the threshold for brittle failure. I could talk about delayed hydride cracking, but it's not, and it's zirconium, so I'm not going to get into that. So I mentioned that one of the modes in which you get the brittle material to the crack tip for SCC has to do with corrosion at the environment, and there are a couple of different models. Most notably that due to Digby-McDonald and the Ford-Andresen model, which essentially the main difference these are the wrong way around. This should be here. Damn it. These should be swapped. Apologies. This is the Ford-Andresen model, and this is the Digby-McDonald model. I'll correct that for the presentation. So basically it's about creating a brittle oxide at the crack tip and then advancing the crack through various means as to propagate the SCC process. So one of the things that is popular in terms of a known effect on the susceptibility to SCC is chromium depletion at grain boundaries. And this typically occurs because of carbide formation. When a carbide forms at a grain boundary, I mentioned earlier, I showed you that carbon precipitates on grain boundaries, carbide former there. And chromium is a strong carbide former. It also is a fast diffuser. So you tend to get chromium being depleted when you get carbide formation at the boundaries. And this leaves you then more susceptible both to corrosion and intergranular attack by various species. So what happens in the reactor? Well, there's been quite a bit of work on SCC, IASCC, and I should call this IASCC. And this is a summary of some work by Brummer et al. Showing that once you irradiate a material, you can get a condition where you get some depletion of chromium at the grain boundary. Now, ostensibly, one would, parsimony principle would state that, well, what's the obvious reason for that? And one would be carbide formation. But in the absence of carbide formation, the other way that you can get some chromium depletion is if there's some type of inverse Kirkendall diffusion, if the grain boundary is a sink for vacancies. Because chrome is a faster diffuser than this element, nickel, for instance. These tend to diffuse substitutionally, so they will segregate the boundary. But what we're talking about is, in this particular case, is chromium depletion relative to these other elements. So you get chromium depletion. And for that to happen, the chromium has to be diffusing away from the boundary if it's not forming carbides. So Brummer et al. Explained the depletion as an inverse Kirkendall effect, but they didn't really get into the mechanistic part, which would help you understand how the grain boundaries are net sinks for vacancies. I mean, you could say that the grain boundaries are simply sinks for vacancies. But often it helps if there's something clear there that can tell you that that's the case. And one thing I noticed, bearing in mind that this was in 1999, this is pre Fukuya and pre-Denny Edwards. What I noticed on the micrograph that went with this plot, you notice this light band here. Well, to my experienced eye, that looks a lot like a string of cavities on the grain boundary. So if you enhance the contrast a little bit, one could see that, yeah, there's something there. Now, you may argue that this is some weird ghosting effect due to misalignment of the microscope, but if this microscope is reasonably well aligned, in fact, it doesn't look that great, because, I mean, there's some evidence of some spherical aberration there. But this contrast to me smacks of a string of cavities in the same vein as, oh, there we go. It's what we see here. And this is now well accepted. We have cavity segregation at a flux symbol in a PWR. And who knows, it may be worth revisiting this now that we have the benefit of hindsight, knowing what people like Edwards and Fukuya have come up with, to revisit some of these earlier cases where there was no real mention of cavity sinks on grain boundaries. In the same vein, there's quite a bit of good data showing chromium depletion on grain boundaries in steels as a function of dose. And in this particular case, this is a depletion which may be from that kind of thing. But the other thing that comes to mind is that if you look at the starting material for this data, this is for is this 316 stainless steel? I can't remember. 300 series stainless steel, where chromium contents above 18%. Now that, to me, tells me that this material has not been sensitized. It hasn't been heat treated to form carbides or whatever it is. It's just a solution annealed material. So this is your starting average composition within the stainless steel. So we have a solution annealed situation, and then we essentially stick it in a reactor and cook it for 3-5 years, something like that. Now, you may say, well, this is 300 degrees C, you don't have enough diffusion going on to form any carbide formation or anything in order to create that sensitization. However, if you calculate the effect just with some nominal microstructures, if you calculate, one can calculate the effect of irradiation on the enhancement of diffusion using a ray theory model. And this is what I did using some data for diffusion from for iron 22% chrome. And then what you see is that you could very easily get a situation where, even though you're at 300 degrees C, the effective irradiation, albeit variable depending on what the microstructure is, the effective irradiation is to put you into a zone which is the equivalent of being between 500 and 600 degrees C. Now you may say, well, 500 and 600 degrees C isn't enough to form any carbides at the normal annealing temperature of a component, 10 hours, something like that. But we're not talking 10 hours, we're talking 300 hours. Sorry, thousands of hours. We're talking years. And so here's just to illustrate, if we pick the top temperature there, here, roughly 550 degrees centigrade, something like that, or even close to 600 degrees centigrade, 550 degrees centigrade. What that would mean, well, if you're in that condition, it would only take you 1 month in a PWR before you get quite substantial carbide precipitation. Now, I think we're more likely to be down here somewhere, in which case a lot longer to get significant carbide precipitation. And it will vary because these curves change as the microstructure evolves. Okay, so just to generally this is I took this off the internet to simulate irradiation. This is stress corrosion cracking. Typically what you have is neutron irradiation, the gamma rays ionize the water and help the stress corrosion cracking in that way. Irradiation comes into play because of the this strain localization type factor and how that interacts with the typical crack blunting that would occur from emission from a crack tip. Anyway, there are a number of different things that come into play. And I just put this in for the sake of it. So when it comes to the ISC, the fluence dependence, here's some data taken from one of the environmental degradation meetings, showing how SCC rate oh yeah, so this is a propensity for SCC formation as a function of fluence, and the propensity goes up with increasing fluence. And there's some data from Gary Was showing how the that same propensity to increasing SEC observation will correspond with other things that are affecting the material. In the material condition here, we have chromium depletion and strengthening, which leads to higher hardening. So the implication here is that you have chromium depletion, which can increase the intergranular track, and hardening, which can also result in higher crack rates, I guess, because you end up with an effect then on the plastic zone at the edge and the end of a crack tip. So put this together. Here's a summary from this report, the CEPA report. If we think about the initiation of stress corrosion cracking, so bearing in mind that this is the propensity for seeing cracking, how often you see it in welds. Let's look at the initiation. From an initiation point of view, there's an indication that higher stresses increase the initiation. So it reduce the dose or the time one needs to initiate cracking, and that would be similar to this hardening effect. But we have this other set of data where they look at the percent of yield stress on the time it takes to initiate cracking. So on the one hand, on the left-hand side, we have this increased applied stress, increased time. Sorry, it should be decreases the time to initiation. On the right-hand side, that should be decreases. Apologies. Decreases the time to initiation. On the right-hand side, for a given applied stress, increase in the yield stress. Increase in the yield stress will take you down over here. If you increase the yield stress for a given applied stress, you increase the time to initiation. So on the one hand, how does that tally with this kind of thing? Well, clearly the initiation is the role of hardening on increasing the potential role of hardening and increasing the propensity for SCC. So that's when you would absorb it. Probably has more of an impact on the crack growth rate. I'm going to finish now the last one on ductile to brittle transitions in the ferritic and martensitic stainless steels. Here's a typical slide that many of you have seen, that if we look at impact energy as a function of temperature, FCC metals tend to be quite ductile, whereas BCC metals tend to exhibit this transition in ductility, where at low temperatures they become quite brittle. The impact energy needed to fracture the material is lower. What happens when you irradiate? Well, irradiation does a couple of things. One, it increases the yield strength. And this is how the yield strength varies with temperature anyway. And it may decrease the fracture stress. So bearing in mind that one measure of ductility, of fracture strength can be determined by, if you think about nil ductility, the closer that the fracture stress is to the yield stress, then the more brittle the material is. It's gonna fail fracture at a lower stress than it's going to yield. So we have this condition where, as the yield strength goes up, the point at where the fracture stress is below the yield stress is observed at higher temperatures. So if at the same time you lower the fracture stress, you shift this transition further. And what that means is that you get a gradual two contributions then to the shift in the transition temperature. And the transition temperature is given by the intersection of the yield stress line and the fracture stress line. So as we go to higher temperatures, that's naturally not a good thing. So bad idea. Oh, I just said that. I should have gone through these. Okay, and then finally, how does this relate to stainless steels? As you know, most ferritic steels or low alloy steels are pressure vessel, and I haven't talked about them. So that's normally where one talks about ductile to brittle transitions. But in the case of HT9, which is a ferritic stainless steel, which is used in nuclear applications, sorry, we have this. We have to be concerned about this if it was used at a temperature or if it was to be operated at a temperature which would be quite low. So when you shut the reactor down, you may have a point where it gets to a low enough temperature that this transition would be a problem. But in terms of operation, you don't want to be too close to this in terms of operation, but HT9 is generally a candidate material for Gen 4 reactors, which are typically high temperature. So we're over here anyway when it comes to HT9. So the inherent embrittlement of the HT9, which is a stainless steel, is not such a big deal. So to summarize, steels are strong, ductile materials that are widely used in nuclear reactors. Radiation damage in the form of dislocation loops and precipitates in cavities increases the strength of irradiated material and reduces the ductility. Ductility reduction and softening is associated with localized deformation, channeling, and sweeping out of dislocation loops, creating a layer of finite width parallel with slip planes. Intergranular embrittlement is severe ductility loss that is associated with helium segregation at grain boundaries. SEC and IASC are dependent on the corrosion environment, the corrosion susceptibility, and the mechanical properties of the material, notably the yield strength. Yeah, notably the yield strength, but in the case of chromium depletion, it would also be the propensity to have attack. Chemical attack or corrosion attack at the grain boundaries. It's a very rapid review of steels, covering a large area that any one part of this presentation could be a whole new presentation on its own. So forgive me for rushing through some parts, and that's all we have. Thank you.